Find the magnitude of the electrostatic force between 2-point charges of 3000 microcoulombs each, which are separated by a distance of 9 meters. Okay, so let me draw a rough diagram here. So these are the two charges we have here, and each of them are of the magnitude, and I want to remind you that 1 microcoulomb is 10 to the power minus 6 coulomb. It's just a shorthand to write that. Okay, so how much would be 3000 microcoulombs? Well, I believe that 3000 microcoulomb will be equal to 3 times 10 to the negative 3 coulomb. You can calculate that yourself. So this is 3 times 10 to the minus 3 coulomb, and this is also 3 times 10 to the minus 3 coulomb. So and these are of the same polarity. So there will be a repulsive force between them, whose magnitude we have to find out. So let's say that is the repulsive force, and they've given us that this distance here is 9 meters. Okay, so in my last video I told you about or I just gave you the formula. It is that the Coulomb's law, which says that the force between 2-point charges which are separated by a distance of r, and the two charges have the magnitude q1 and q2, is given by some constant k times the product of the two charges q1 q2 divided by the square of the distance between those two charges, so by r squared. So I just gave you some intuition why this is so. This is actually derived experimentally, so we have no formal proof for this. There might be, but at least I don't know it. So if we go by this, if we consider that the Coulomb's law holds for this case here, then the force between the two charges, if I call this one F, the force between these two charges according to the Coulomb's law will be K. But I believe I told you the value of that K, which is also derived experimentally. Its value comes out to be 9 times 10 to the 9th, then multiplied by the product of the charges, but they are of the same magnitude, so I can just write it once and square, right? So this is 3 times 10 to the minus 3, and we can write again 3 times 10 to the minus 3, but I won't, because we can just square this. Okay, so and divided by the square of the distance between them, right? And the distance between them is 9, so r is 9, so 9 squared will be 81, right? Okay, so let me scroll down a bit. So we have 9 times, let me change the color, 9 times 10 to the 9th, this is a 9, and you can calculate this is 9 times 10 to the minus 6, I believe, yeah, divided by 81. Now you can see that 9 times 9 is 81, but we have an 81 in the denominator, so that cancels out. So the final answer comes out to be 10 to the power 9 times 10 to the power minus 6, which by exponential properties is 10 to the power 9 minus 6, which is equal to 10 to the power 3, which is undoubtedly 1000 newtons. So there is a force of 1000 newtons, which for me at least is a huge force. It is the weight of a man who's we could say he weighs 100 kilograms on the weighing machine. So you can imagine that. Yeah, I'm actually 65 or something, so you can imagine 100 would be very large because I'm very fat. that was just a joke, but 1000 newtons is, yeah, an appreciable amount of force. So you can see that just by 3000 microcoulombs we have such huge amount of forces. So you can imagine that 1 coulomb would be an huge amount of charge. I mean, I have no example for this, but it is truly a very large unit of measuring charge. So that's why we introduce all these micros, nanos, picos, farads, sorry, not farads, picos, etc., which have a relation just like this, where micro has 10 to the power minus 6, pico will have 10 to the power minus 12, and pico is also called micro because if you put 2 micros, it will be 10 to the power minus 6 squared, which is 10 to the power minus 12, and we call that pico. And similarly, we have nano coulombs, which is 10 to the power minus 9 coulombs. So practically, we will be working with charges around this range only. So for all practical purposes, this force can be feasible. So I guess that's pretty much it for Coulomb's law. It is not of much practical use, but it is the basis of electrostatics for theoretical purposes. Because I told you in my last video, this force applies, this law applies only to static charges. That's why we call it electrostatics. So in real life, there is very slim chance that you'll work with stationary charges. So it's not of much use in practical things, but yeah, it forms the basis of some more advanced laws like Gauss's law, which is just an advanced form of Coulomb's law. I'll discuss that later after dealing with electric fields, electric flux, and etc. Don't worry if it doesn't make any sense now. It will eventually. Yeah. So in my next video, I'll talk about electric fields, which is also derived from Coulomb's law only, as I'll show you. Then we'll move on to more advanced topics. So yeah. I hope you like it, and I'll see you in the next video.